Okay, we're going to go ahead and start. Okay, yesterday I gave you information about an orbital. An orbital is just a three-dimensional space or area where the electron is going to be most probability you're going to find electron within that space somewhere. High probability. Okay, so that's called an orbital. Right? That's where the electrons are going to be at. And if we're talking about a house, for example, this would be like your bedroom, where you hang out a lot of the time, right?
Yeah.
Sleep there, maybe do your homework there, whatever the case might be. But that is what we call, that would be kind of like if we take a look at analogy, that would be like your bedroom in your house, right? And then we'll kind of use that as an analogy, and you're kind of like electrons and try to bridge it back and forth, right, with some examples. So the first one we had talked about is called the principal quantum number. Must have moved on me. Having trouble today. That's symbolized with an N. Is that right?
Yeah.
Okay? And what that N tells you is going to tell you an N can be called an energy level or shell. So an N describes, if I say the N, if I said N equals 1, N equals 2, N equals 3, that's going to represent the energy of the electron, called the energy level. It's also called the shell, where the electron's located. There's multiple shells that atoms have. And we just give that description because we know a little bit about shells, that we got an outside shell or inside shell, like for like a peanut, for example, an outside shell. We know a little bit about that. Yes?
So is this like the E1, E2 thing?
Kind of, but we're going to transition the E1, E2. We're going to use a similar model for it, but it's not going to be the same thing. Okay, it's not going to be the same thing because those energy level, when they move, that can be within the shell itself. So we're going to just talk about we use a similar setup to show that, but it's not going to be the same. All right, so that describes the energy level or the shell that we'd have. And if we remember, you had numbers out to the side that were positive integers. So they would be 1, 2, 3, so on and so forth. Okay? And they can go up to whatever number until you run out of electrons. We only have 90-something electrons that we're dealing with. And so what the principal quantum number describes is the location of the electron as well as its energy that it has. So it describes two things about the electron. It describes the energy of the electron and its location relative to other electrons. So this is all relative. Okay, when we do this, we're not going to say, well, it has this exact amount of energy, 3.0 times 10 to the minus 19th joules. But what we will do is we'll give you a model to kind of take a look at and show where the shells are. So this is our first description of the electron. It's kind of like the address would be Beatrice, Nebraska. Be like Beatrice, Nebraska. So it's a general location of the electron, or parts of town. Well, I live on West Court. I live West Court area. I live in what, the Belvedere area. You know, so we have different sections of town that we might be able to describe. And that's kind of like the principal quantum number. It's kind of a general location of where the electron is going to be. All right? Any questions with that? So let me go ahead and show you a model. You can write this model right underneath if you have room, because I told you guys to make sure you left enough room. And it's going to be similar to what we have dealt with about the E1, E2 and that. But we're not going to use E1, E2 on this. We're going to go ahead and list these shells out. This is the first shell or first energy level. This is the second shell or second energy level, third and fourth. All right. So as the principal number increases, what do you know about its location? Farther from the nucleus. So we know that a 2 location is farther from the nucleus than a 1. So we can think of, for example, the courthouse being the nucleus, or being where a lot of stuff takes place in the county. And then locations away from that area would be further and further away, distance-wise. And each one of these locations require more energy. Right? So a 4 has electron in a 4 requires more energy to be in that location versus a 1. They have to have more energy to be out there. Okay, any questions? So these can be shells, 1, 2, 3, 4 shell, or they could be energy levels, first energy level, second energy level. That's the way I will describe it. And that's the way that you will read about it. Okay. Sometimes they'll say levels in your book. Any questions? So it's just a general location. Tells about relative energies and relative position compared to other electrons. Doesn't tell us anything about the shape. That comes next. So electrons will travel around the nucleus in these things called orbitals, and then those orbitals will have different shapes associated with them. Just like everybody in here will live in a house, and that house will have a different shape to it. Different number of rooms. Some of us might live in a house that's a 2-bedroom. Some of us might live in a house that's a 5-bedroom. Okay? And so each location of electron might be in a shell that can hold a bunch of electrons, like a big house would, or it could be in a small 1-bedroom house, example, that holds fewer electrons. So these shells, depending upon the size of them, they can hold different number of electrons. The analogy that I would say is like, for example, a motorcycle. How many people can fit on a motorcycle? Comfortably.
Does that have a side door?
No clowns involved or anything like that. 2, right? 1 or 2. If you got just a regular mid-sized car, we're talking maybe 5 or 6, right? We talk a school van. They're probably taking school vans up to the softball game. How many?
8.
They can hold 11. 10 and a driver. They can hold. All right? And so, bus, of course, holds more than that. So as we work our way out, each orbital has more space and it can hold more electrons. As we work out from 1 to 2, 2 to 3, 3 to 4, it can hold, that particular one can hold more electrons. Okay? So it describes the energy of an electron and its location relative to other electrons. All right. So then we get to our next one. It's called angular momentum quantum number, right? And that's symbolized with an L, correct? All right, so, and I had you write down off to the side, shape. There are 4 different shapes that electrons can move within that shape around the nucleus. Okay, and these are the shapes. 4 shapes. They're the S, P, D, and F. Now, principal quantum numbers, we can say energy level or shell. The angular momentum quantum number, what we can do is we can talk about that as what's called a subshell. So a shell within a shell, a subshell. And that subshell, we can say the S subshell, P subshell, D subshell, or F subshell, because that's what those letters represent. Okay. So it's kind of like rooms in your house. You have 1 room, 2 rooms, or 3 rooms. Those rooms have different shapes, but you can have multiple rooms there. So we have 4 shapes, and the first shape is an S, and it's a sphere. Right? So, like this balloon, that is an S shape. That's where the electron is going to spend most of its time, is within this part of the balloon. Right? So that's where the electrons are located. Any questions you have on that? Okay? That is the first shape. It's a sphere shape. Then the next one is a P shape. And it is a dumbbell. The dumbbell's like the infinity sign.
Like an 80.
Kind of like figure 8. And then this is an example. Ooh, get away from me. This is an example of a P subshell. See, we have an S, which is sphere, and now we got kind of a dumbbell shape, right? Dumbbell. Working hard today. All right, so that's the shape. So what we're doing with these, with the angular momentum quantum number, which is called a subshell, we have 3 or 4 possible subshells, S, P, D, and F, and they all have different shapes. I cannot show you D. I can't show you F. They do have D in the book that you can look at. All right? Now I'm going to also tell you something about these, is that energy-wise, and this goes underneath this too, an S is less energy than a P, which is less energy than a D, which is less energy than an F. Okay, when we look at energy that they have.
So F has the most energy.
Yeah, F has to have the most energy. All right. Another thing I need to tell you is where they're located. So the S's will come in the first shell. That's where we see them. They come in the first shell. They are in the first shell. And then
Wait, what about the subshell?
the S is a subshell. So the S subshell is in the first shell. Okay. Then the P will come in the second. The D the third. And the F the fourth.
What's 3 F's?
I'm not going to show them to you. They're in the book. They're really, really complicated. They get really kind of out there, and they don't even show the F's. All right? So I'm just going to go with the S and P, and that kind of gives you enough information to know that they have different shapes. They have different shapes. The S is also in all of them. So the S will be in the second, the S will be in the third, the S will be in the fourth. It's in all of them.
So what would P be in the alpha?
Yep. And the P is in the second shell, but not in the first.
So it starts in the second shell.
It starts in the second shell. Yep. And the D starts in the third shell. And the F starts in the fourth shell. And so on and so forth. Okay? We can put there, starts. Okay. So we're going to start getting more shapes. Each shell we get one extra shape of a type of orbital that we'll have. Any questions with that? So we got shells, 1, 2, 3, 4. They tell you the location of the electron relative to other electrons, and they tell you the energy. As you go out, they get greater. The S, P, D, and F also works the same way in energy. S is the lowest energy level, or subshell, than P's a little bit more energy needed to be in that subshell. And where they come in. S comes in the first, P comes in the second, D comes in the third, F comes in the fourth. All right. So you kind of got that figured out. Now, we're going to introduce probably the most important one to try to put all this together, and it's that magnetic quantum number. It's symbolized with an M. And I've had you put down orientation. I'm going to go ahead. You can add to that if it makes sense. Orientation or pathway. So when you come to school, there might be different, some of you, there might be different ways to get to school. And we have two different ways to get to school. We have an alternative route, which wasn't always there, but allows some of the traffic to flow in two different ways so it doesn't get all plugged up at the stoplight. There's two ways in that you can have. Is there a third way in? You know of a third way in. What's that? Grass, but not a road that's
The Dylan Harms.
the Dylan Harms way. What way does he take?
Grass.
He goes through the grass.
Sidewalk.
Okay, so just where there is a road that you can come in, there's two ways. So
You can take the sidewalk.
when we take a look at the S subshell, it has only one pathway. And I'll show you a demonstration of this with the balloons. The P has 3 pathways. So the S subshell has one possible pathway around the nucleus. The P has 3. The D has 5. You guys gonna know what the pattern is here? F has 7. 1, 3, 5, 7 pathways around the nucleus. Okay. And those represent orbitals. So the S has one orbital. The P has one shaped orbital, but it can have 3 pathways. So to show you that, I have balloons. And these balloons all have the same shape, right? They all have the same shape. So these would represent what subshell?
P.
P. This is the sphere shape. It only has one possible orientation around the nucleus. What do we mean by orientation? It means that if we would put the P subshell like this, it would be along the z-axis. So we'll have the z-axis, vertical. Okay? Then we'll add in the y-axis. there's the y-axis. So same shape. Oh,
I thought you were gonna start twisting them.
okay. So there is the. That would be like the y, and then we got a z-axis that we'll do. When we put them all together, we have the same shape, but 3 different pathways around the center, the nucleus. Same shape, 3 different pathways. So when I talk about pathways, the electrons are not occupying the same space, but they have the same shape. Any questions with that? That's orientation. That's what we're talking about. That. Now we're not going to show D's, but if we did have D's, they would have 5 different pathways with the same shape. And the F's would have the same thing. So it gets really complicated.
So they like different dimensions or something?
Nope. Well, I don't know what you mean by dimensions. They take up a different space. See, they don't occupy the balloons cannot occupy the same space, but they have the same shape. So the P shape is the same for all 3 of them. They're just different ways in which they go around. All right. Now I need to tell you that each orbital, each one of these orbitals can hold a maximum of 2 electrons. So each orbital can hold 2 electrons. So how many electrons are we talking about in the S?
2.
2 electrons. How many can the P subshells, if they're all filled within an energy level, how much can they hold?
2.
They can hold 2 apiece,
6.
and I've got 3 here, so that's a total of 6 electrons. All right? D, 10. And the F's can hold 14. Now, if you look at the periodic table, there are sections that have 2, blocks of 2, blocks of 10, blocks of 6, and blocks of 14. Can you find the block of 2? This block, here's 2. Going across. There's 2 in that block. Okay? Where's the block of 10?
The transition
10 across, right? Transition elements. Okay, where's the block of 14 at? Block of 14. Okay? And then the block of 6? So we're going to use the periodic table to describe where electrons are at and kind of give them an address starting tomorrow. But today we're just kind of getting all the specifics about these electrons. We know the energy level, we know the shape, now we know the orientations and how they kind of occur. All right? Now each electron within a shape has to have an opposite characteristic. It's kind of like in your house. Jared, in your house, everything's going to be the same that sent letters out for you and your sister except for what? When you get an envelope from the school.
They're going to be my name.
Your names are different. Everything else is the same. You're in the same household. You get the same mail. The only thing that's different is your name. So electrons that are in each orbital, which are 2, they have to have opposite spins. So that's when we get our spin quantum number. So these electrons in the same orbital with opposite spins. They can't have the same spin in the same orbital. And the reason why is because when we talk about spin, it's like spinning on a top. In clockwise or counterclockwise, like spinning a basketball. Clockwise, counterclockwise. That's an internal spin. And they can coexist in the same space if they have opposite spins. If they have the same spin, it's not going to work. They were going to repel each other. Opposite spins allows kind of what's called a magnetic property to allow them to coexist in the same space, small space. Okay? Any questions that you have? So, let's just take a look at, real quick, just some information, kind of putting everything together. You don't have to draw this. What shapes are in the first shell? Or what subshells are in the first shell? An S. What shapes are in the second shell? S and P. Both. The P's come in the second, but the S's are in everything. Okay, the third one is going to be
SPD.
SPD. And the fourth?
SPDF.
Each of these can hold, each subshell, we know how many can hold. So how many electrons are in the first shell? 2. How about the second?
8.
6 and
2.
2 is 8. If you look across the second row and you count, there's 8. You go across the first period, there's 2. You go across the second period, there's 8. And then it kind of messes up after that. But you go across the fourth row, how many do you have? 18. And across the, I guess would be one of the last rows that's full, how many are we talking there? 32. So 2, 8, 18, 32 is how much they can hold in there. Okay? So I have a worksheet that I'm going to give you. Some of this is going to be repetitive. I know it takes a while to get this down.